Microsoft Excel, which is part of Microsoft Office, is a very powerful software tool for keeping track of large amounts of data, sorting it, plotting it, and manipulating it. And I want to introduce Excel in the context of the slider crank example. So here's a previously discussed slider crank mechanism where the continuously rotating crank drives a toothed rack back and forth and gives reciprocating motion to a gear, which could be part of a washing machine agitator. Or if we delete that gear and toothed rack, then it starts to look like one cylinder of an engine. Just as an introduction to Excel, I'm going to label these points. Point O is a fixed point on the base. A is the end of the crank. I'm going to assume that the crank length is given the variable name R. We'll give the connecting rod variable length L. And we'll say that the piston has a mass M. And we'll call this pinpoint down here point B. The engine shaking forces, if this is an engine, or if it's a compressor, the compressor shaking forces, are related to the acceleration back and forth of that mass, which moves with point B. So our goal eventually is going to be to plot the distance xb as a function of the angle of the crank link, which I'll call theta, and also to plot the acceleration as a function of the crank link and see if any interesting things happen. But first, in order to do this plotting and get used to this Excel package, let's just focus on the crank itself. Okay, and let's plot the x and y components of point A. Alright, so we'll assume that we have an origin at point O, and I'll draw x and y axes. So point A's coordinates are x and y. If this moves in a circle, we would expect x to be distance r times the cosine of theta. That would give us this distance x, and similarly the y component, if we imagine this as being a right triangle, y is going to be distance r times the sine of the angle theta. And that theta should be maybe tucked in a little bit closer to indicate that it's the angle that the crank makes with the horizontal. Alright, so let's plot x and y versus theta or versus time. Suppose that we give this crank a constant RPM, constant rotary speed. So we're defining the angle theta. Usually, I think most of us are comfortable expressing angles in degrees, but we can also express them in radians, where we know that 180 degrees is pi radians from our high school trig. Just to backtrack a bit here, if you had a mass that was sliding on a horizontal surface, and if I was going to measure its distance traveled x, and if I was going to measure its velocity v, if it had a constant speed, so if, for example, v was 10 meters per second, the distance, x, distance is equal to rate times time, so x would be v times t. And the units of that, x we would expect to be in meters. The units of velocity, meters per second. The units of time are seconds, and if we cancel off those units, we do end up getting x, in this case, would be equal to 10t meters. Now the rotational version of distance is angle, and the rotational version of speed is something we'll call angular velocity. Angular velocity, which is often given the Greek letter omega, not to be confused with W, and I'm going to define that in radians per second, which you could easily convert to degrees per second or revolutions per minute, RPM, the speed, the rotary speed unit most of us are comfortable with. We all have a sense that 10,000 RPM is really, really fast for an engine, and maybe 60 RPM, well, your engine will have stalled by then. All right, so if I'm going to imagine this crank rotating at a constant speed, come back down here and I'll redraw it. So here is a fixed point O, a distance r, here's point A, here's the x coordinate, here's the y coordinate. Suppose I set r equal to 0.2 meters. X is going to be r times cosine of theta. Theta is going to be omega times time, in a manner similar to distance was velocity times time. And if we look at the units there, theta in radians would be, let's make omega equal to 10 radians per second. So we're going to have 10 radians per second times time in seconds. Again, the seconds will cancel out. So theta is going to be 10t. And if I substitute that into my equation for x, I'm going to end up with x is equal to, well, let's see, I want x to end up in meters. R is 0.2 meters. Cosine of theta, let's see, the cosine of theta is going to be some number between -1 and 1. It doesn't have any units. So we have simply that x is 0.2 cos theta, and similarly y is 0.2 sine theta. Or if we want to do that in terms of time, x is 0.2 times the cosine of angular velocity omega times the time t, and y is equal to 0.2 times the sine of, in this case I said I was going to make omega equal to 10. So x is 0.2 cos 10t, y is 0.2 sine of 10t. Alright, so in the next video we are going to plot x and y versus time and generate a plot which will hopefully look like a cosine and a sine.